smiling back there. Is she? Okay, that'll do. Okay. I don't know. I just looked at you and I thought microphone. I don't know what it is. No. So, as I say, what I really want to talk about are the principal series. But there's some technical thing about the principal series that I want to be sure everybody understands. So I thought, and that technical thing is motivated by the problems of integration. And so I thought I'd start, and integration is pretty important in the end of the lecture. So I thought I would do that. Wait, let me wait 1 minute. There's something else I have to have. I don't know if the camera was good. The camera doesn't track me when I go over to pick up my notes. So I thought I'd talk about integration on first just on manifolds in general. So I thought I'd start by reminding you, I'm never going to integrate anything very complicated, just very nice, smooth functions. But even so, I thought I'd sort of, there are a couple of technical problems to get through. My co-lecturers advised me not to try to explain this because the technicality is really quite high. But I thought still it's kind of fun. And to tell you the truth, I just figured out what was going on myself after 50 years of integrating. So first of all, let's begin with just Lebesgue integration on Rn. The point is, the problem is this. There are two notions of integration that you guys in principle know about. What are those two different notions? Well, that's... Yeah, the problem is orientation. The whole problem I'm dealing with is the problem of orientation. That's the main problem. So given that fact, what are the two different kinds of integrals you know how to do? Well, just ordinary Riemann integration of a function. And in this case, for ordinary integration, the kind that they give you in analysis courses, you take a set, say a square or a rectangle or something, or a brick in general in higher dimensions, and you assign it a measure. Bang, it's got a measure just like that. And if usually you start with a positive measure because those are the nicest to deal with. There's some convexity properties they have and so on. And it has nothing to do with orientation whatsoever. You just assign a set a measure. But what's the other kind of integration? Form, that's right. You also know how to integrate forms. And so there are these two different notions, measures and forms, and actually on the Rn, they're almost exactly the same, and this is a source of tremendous confusion. But on other manifolds where you don't have an orientation, then things get a little bit complicated. And that complication occurs in the theory of Lie groups and induced representation. So that's the thing I want to talk about. So I'll start just by recalling the measure theoretic definition. So, and the confusion between the two is not helped by the fact that the notation is designed to confuse. Seriously. So if I take a function, so I have a function on Rn, it's compact support, so really we're not going to, I don't say that. Oh yeah, I do say so. So x is a compact set, a relatively compact set. So I just write down the Lebesgue integral, like that, or the Riemann integral, whatever it is, which you calculate. Now, of course, you know how to calculate these things very, very rarely. It's very hard you can actually calculate the integral of a function in Rn, and if you can, almost always it's because you can somehow reduce it to something in one dimension. It's just a fact of life. Now, in one dimension, things are especially confusing. I'll give an example in just a minute. In one dimension, we know how to do things by the fundamental theorem of calculus, but now we're back in confusion land because the fundamental theorem of calculus is really something about differentials of exact differentials and so on. So it's all kind of confusing, and that's what I want to straighten out. Now, the point is that if we make a change of variables, so I set x equal to some function of another variable y, I want to change my variable of integration to y, and that's easy. I just put in h of y here. But then what do I do to integrate correctly? Well, first of all, here's my original support, x, and this changes to h minus 1 of x because x is in x if and only h minus 1 of x is in, whoops. Yeah, that's right. X is equal to hy, y is h minus 1. This, of course, causes terrible problems in calculus courses because calculating inverses of functions is never nice. But anyway, so the integral becomes over a different set, and now there's some change of scale that you have to take into account, and that's accounted for by the Jacobian matrix. And now the thing that's important here is that this bar here, this is the absolute value of the Jacobian determinant. That's the thing that goes in there. And this is the sign that we're dealing here with measures as opposed to forms. If I were dealing with forms, then there would be no absolute value. It would just be the determinant of the Jacobian matrix rather than its absolute value. So that's the key difference between forms and measures, is when you change variables, you have to change either by the absolute value or not by the absolute value. So somehow we have to deal with this difference when we're integrating over manifolds. Any questions so far?
So by partial x, partial y, you do mean in fact Jacobian.
This is, yeah, this is a Jacobian. I mean, who knows, the notation is terrible. I could have written h, but you know what I mean, it's just the Jacobian. So what it is, it's the partial derivatives of h with respect to the different variables of y. So it's that square matrix that I get. Right. And again, the notation is confusing because in where I learned the change of variables formula, the absolute value sign just means the determinant. But here it means the absolute value of the determinant. And I don't know what, luckily I don't have to write the other one, so I won't have to do that. And now the change of variables formula in 1D seems a bit paradoxical if you think about it. So to tell you the truth, whenever I teach calculus, I always get a little confused myself, but no longer. If I straighten myself out, I'm a reformed person. So let's suppose we want to change variables in a formula like this. So we want to integrate from minus infinity to infinity of f of x dx. So that's fine. So we set, and I change variables. I set x equals minus y. And so I change my variable here to minus y. And now I change my dx to minus dy. And that accounts for this minus sign. And then I have to change the limits of integration. And that does this. But then there's some convention that says that what I really want to do is reverse this. And when I do that, I change the sign. And so it all works out. And so this is actually the integral of measures that you're dealing with. Everything in calculus is designed really to do with integral of measures. Just a cute fact. So let's see, how do we integrate forms on Rn? Well, the point is, so if I'm given a differential form, well, abstractly, it's just, I don't know, it is a differential form somehow, and there's some abstract definition which doesn't depend on coordinates. But if I really want to integrate the thing, then I have to represent it in a very special way. I represent it as f of x, and those are multivariables, all the variables x1 to xn, and then I have to orient my wedge product, so to speak, so that it matches the orientation in Rn. So now for the first time, when you integrate forms, the orientation in Rn appears, and you're given this canonical orientation with the right-hand rule in 3D and so on. And then I integrate the integral of my form is just the usual measure theoretic integral of this. Okay. So it all comes down to measure of integrals, but you have to take the orientation into account by this point. Okay. So the next question is, well, Rn. So we know how to integrate on Rn, but now I want to integrate on oriented manifolds. So that's the next stage in this process. Well, let's see. I ask you, how do I, so I'm given a form. How do I integrate that form on an oriented manifold? What's the magic word? I have in mind. Huh? It doesn't tell you how to integrate. I mean, that's important, but it doesn't tell you how to actually integrate. I mean, how? Okay, well, let's see. So I'm given, let's suppose M is an oriented manifold. So I can cover it by coordinate patches. The problem now is if I have an oriented manifold, and we know how to integrate on Rn, I want to reduce the question of integrating on the manifold to integrating on Rn. And so I cover it by coordinate patches. And I arrange that the coordinate patches is an oriented manifold, so I can arrange my coordinate patches all to agree. And they match that of the original manifold M. And I use a partition of unity, phi, subordinate to the covering. And then I multiply my original form by the phi's. So the phi's are smooth functions. I'll say something about these in just a minute, actually, on the blackboard. These are smooth functions on the manifold, but they restrict the support to the coordinate patches. And then these can be identified with forms on Rn. And I have to do some fiddling around. Well, no, that's exactly the way it works. And then I write my thing locally in coordinates and so on. And then the integral over M becomes the sum of the integrals over Rn for the coordinate patches. Okay. Now here's the first serious question that comes up. What's a partition of unity? Miss Turkish student whose name I don't know. Huh? Nilofer. I can't, my eyes are terrible.
My name is
Okay. Nilofer. What is a partition of unity?
Those are functions of manifold such that the sum is equal to 1.
And
They are supported in this.
yeah, that's right. So we need a covering. So what I have is, let's just draw a picture. So if I have, let's take, for example, just the circle. So I can cover the circle by two open sets. So I cover it by these open sets. and this open set. So that's what I need. So a manifold is something I can cover by coordinate patches in a nice consistent way. And now, in this case, so I have these two coverings by open sets. I don't have to cover, let's do a better job of covering, actually. So we just have to cover like this and maybe like this. And now a partition of unity means I take two functions such that sum is 1. So phi1 plus phi2 is 1, and this is my set u1, and this is my set u2, and phi1 and phi2 are smooth, usually restricted. You usually restrict them because almost always you make some convexity, or very often you make a convexity argument. You need the fact they lie between 0 and 1. The sum is 1, and phi I has support on ui. Okay, so that's what a partition of unity is. How do you know that partitions of unity exist? What's the key fact? Yeah.
Manifolds are paracompact.
Oh, I've forgotten what paracompact means. I haven't had to worry about paracompact since my first year of graduate school. I'm not going to begin now. Every manifold I ever look at is definitely paracompact, I'm sure. What's the key elementary fact from calculus that you need to know?
Exponentials decrease really fast.
Yeah, you need to have enough functions that look nice. So what you need is, you need to know that functions like e to the minus 1 over x, for example, look like this, that they're extremely flat at the origin. And then you can construct functions. So you start with functions like this, and then by fiddling around, you can get functions that look like this, that are absolutely 0 here and non-zero here. And that's the key start of the process. Beyond that, it's technicalities about paracompactness and so on. Okay. Actually, the existence of such functions plays a key role in representation theory. I don't think we're going to get around to that anytime. Okay, so that's how to integrate on an oriented manifold. The point is you have to arrange that the coordinate patch is oriented right. Okay, now, suppose I want to talk about measures on an arbitrary manifold as opposed to integrating forms. So the problem is this. So I have an arbitrary manifold of dimension n. And M might or might not be orientable, or it might not, well, it's not oriented because I haven't fixed an orientation. So what does orientable mean? Yeah, what does it mean to orient it?
There's a non-vanishing section. There's a non-vanishing top degree exterior.
Yeah, I guess that's one way to put it. So an oriented manifold is one where I can just find a differential form that doesn't vanish anywhere. That's true, but there's a slightly more technical definition which is more convenient to work with. Namely, I have what's called the orientation bundle. So if I have M goes to its orientation bundle. I mean, how many ways to orient something are there? 2. So I want a bundle with 2 elements. How do I get a bundle with 2 elements on the manifold?
You define it by patches. You take
No, how do I, this is actually a purely canonical way of doing that. How do I get a bundle with 2 elements on it? Huh?
Just take 2 copies of manifold.
Yeah, but how do I get those?
At every point, we have 2 orientations of the neighborhood of that point. That's the final.
That's right. So well, actually, technically, then the way to work it is if I have x a member of M, then that goes to the wedge product of the tangent space. I take minus 0, and I divide by the positive reals. Okay. And this has 2 elements. So this gives me a new manifold. So what I have is it's a little hard to describe, but if you look at a cross-section of the Möbius strip, for example, it looks like this. Here's my original manifold. Then over that, I have sitting a subset of 2 elements. This is a fiber bundle. At every point, I just have these 2 elements. And when is the manifold orientable? When I can take a section of this. So M is orientable.
Could you explain that construction?
I surely will. Hey, hang on, I'll let you. Well, I'll call it, I don't have a plus or minus 1, so I just have, I don't know what to do. I have 2 elements, epsilon 1 and epsilon 2. Yeah, well, it's sort of equal to plus or minus. But there's no canonical way of assigning it. And so an orientation means I can go back. Let's see, I have 2 on my stack. I have 2 questions. Somebody asked me to go over it again, and then somebody had a comment. Did you have a comment?
bundle associated with the orientation or the top degree forms?
No, because I'm dividing by the positive reals.
Oh, right, yeah, okay, right.
Right, that's exactly the crucial point, is I'm dividing by the positive real, so I get two elements. If I divided by the scalars,
Yeah.
this is a one-dimensional thing, right? So the whole point is I get two elements instead of one. Okay. And somebody asked me to do this again. What exactly would you like me to see?
Just why is that
Yes?
why is that space of exterior forms minus the 0 divided by the positive real? It doesn't make any sense to me.
Sure. I mean, that's fine, because I love students like you, because my generic rule in life is that if one student has a question, then there are actually 50 students who have the same question, and they're just far too embarrassed to ask. So I love people like you. It's just really great. So, okay, so let's look. It's not that kind of love. It's not. So, okay, so we have a manifold M. It has dimension n. And what's the wedge product? Remember what the wedge product is?
What the dimension is, or what the wedge product?
What's the wedge product?
I know what it is. Alternating forms.
Yeah, it's alternating forms. It's not alternating forms. It's the wedge product of the tangent space.
Right, it's alternating forms of the tangent space, so it's.
No, it's not alternating forms. That's not right. What's the relation between alternating forms and this thing? It's dual. Yeah, this is just the alternating vectors.
Yeah, right. Yeah.
Okay. And the alternating vectors I get from tensor products and blah, 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 blah. Okay. So this thing has what dimension now?
And choose n to the 1.
Yeah, what's n choose n?
1. Okay.
1. So this is isomorphic non-canonically. It's isomorphic to this. It's said to be a homogeneous space over R, is what they say. And so if I subtract off this, so what we have is the following situation. I'm looking at, here's one orientation, there's the other, but the point is that it is a homogeneous space over R, not canonically. It doesn't have a canonical choice. So and in fact, on the Möbius strip, for example, if you start out like this, you get around like this. So there's no way of assigning orientation to that point. Okay. That's right. But I don't know which is positive and which is negative. That's the whole point. In order to decide which is positive, which is negative, I have to take a section if I can, but you can't always take a section. Okay. So I get this covering. And the manifold is orientable only if this bundle has a section, continuous choice of orientation, blah, blah, right? If it's orientable, then we can integrate forms over it. But in order to integrate the form, I have to choose the orientation. That's the trouble. This is not quite the right idea. So we don't really want to integrate forms. As we saw, somehow there's some confusion between forms and measures. We don't want to integrate. I want to somehow get the notion of a measure on the manifold. I can't integrate forms because I have to choose the orientation. And not only that, but choosing the orientation is crucial. If I change the orientation, what happens to the integral of the form? It goes to its negative, because remember, in integrating forms, I always arrange the form so it matches the orientation. If I change the orientation, it changes the sign of the integral. So we don't want to integrate forms over the manifold. That's not a good notion, because I have to choose the orientation first. I want to somehow get the notion of a measure. So as I say, there's no canonical way to integrate forms on M. But M tilde is oriented. M tilde has a canonical orientation. I didn't say that, but that's because it's 12 o'clock at night, and I wrote it down. So this is the key thing I didn't put on the side. I'll write it real big. M tilde has a canonical choice of orientation. This statement holds bang, just like that. It's absolutely true. Let me convince you it's true. So here's my M tilde. Locally, of course, M tilde looks like this. There's no problem. And here's my M down here. And now the tangent space is the same or here. So I certainly have an identity of tangent spaces here. And now up here, I have two orientations. So here's my orientation here. But now this corresponds to a choice of orientation here. So there's a canonical orientation on this space here. Actually, it should probably go the other way just for, otherwise I'm going to run out of room. So the two fibers, so to speak, over this, corresponding to two different orientations of this tangent space, but this tangent space is the same as each one of these tangent spaces. So on this thing, there's a canonical orientation. So I don't have any choice. It's absolutely canonical. So I can integrate forms on M tilde. So there's no problem. I think I did state that on the slides. Yeah. Oh, no. Yeah, okay, so I didn't say that. So there's a canonical way. Because all I need to integrate forms on M tilde. Okay, is everybody with me so far? Yeah.
Why is this so canonical? Why can't you just flip these arrows?
Because the tangent spaces are the same, right? There's certainly a canonical identity between the tangent space here and the tangent space here. I just project down. But by definition, the fibers here on M tilde are a choice of orientation on M. That means it's a choice of orientation on the tangent space down below. But the tangent space here is equal to this tangent space, so this comes fixed with a given orientation on this tangent space. Absolutely canonical. Okay. So what you might think is, well, suppose we want to integrate a form on M. This doesn't work, but we'll see what goes wrong with that. If I want to integrate a form on M, it's very simple. I pull back the form to here, and I integrate it over M tilde. What happens then? I get 0. Because the integral over here and there, these two cancel out immediately, so I get 0. So what I can't do to integrate over M, so to speak, I can't just lift a form up to here and integrate it. And that's because the form I get is symmetric, right? I have an involution on M tilde, interchanges the two fibers, and it changes the orientation. So I can't look at the form. So now what I do is, it turns out that the correct answer to the puzzle we're trying to solve, how do I define measures on M? The answer is, I look at forms on M tilde, which are taken to their negative by the canonical involution. So M tilde. Yeah.
Could you give some example on M tilde, like if M is Boolean span or real projective space?
I'm going to give some examples later on.
Oh,
Okay. I mean, to tell you the truth, we're only interested in one example, and that's SL2 quotient. That's the projective real line, or actually in general, you might as well look at projective real spaces. Okay. Okay, but still, it seems, my colleagues, my co-lecturers said this is all unnecessary, but there is a little trick for principal series that somehow I wanted to analyze. Okay. So, I think this is on the next slide. Let's see. I didn't say the crucial. Oh, here we go. I just skipped a page. So M tilde has a canonical. So far, I haven't gotten an email from anybody telling me about the errors on my notes, except one guy, and he actually fudged he dodged. He was embarrassed. He just hinted that I had an error. Okay, so it has a canonical involution, interchange in the orientations at any point of M, and the N forms on M, blah, 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 blah. Yeah, the N forms on M, when I lift back an N form on N, I get an M form on M tilde, and it's invariant under the involution. So I define, and since changing orientation changes the sign, I just get 0, so that's not what I want. But now I have the notion of a twisted N form on M, and a twisted N form on N is equivalent to an N form on M tilde, which gets interchanged to its negative under this involution. And it turns out that that's basically how to define measures. So the measures, so by definition, a twisted N form on M is defined to be an N form on M tilde that's taken to its negative by the involution. And now, if I want to integrate, suppose I want to integrate a form, one of these twisted N forms, and then I define its integral. So its integral, this thing is basically a form on M tilde, which is antisymmetric, and I define the integral, its integral over M to be 1/2 its integral over M tilde, which I can do because M tilde has a canonical orientation, and therefore I can integrate forms canonically. Okay? Yeah?
Does this allow us to integrate all N forms over the
No, it allows you to integrate twisted N forms, and it's a measure. Basically, twisted N forms are measures. It's the twisted N forms of the replacement. So I have this notion of measures. Measures becomes kind of vague when you don't have a canonical coordinate system. But still, so the twisted N forms are the replacement for measures on an arbitrary manifold where you don't have canonical coordinates. So what you integrate on a manifold are twisted N forms. Sometimes they're called densities, sometimes they're called measures. Everybody has his own terminology, but twisted N forms, I don't know whose term I may have learned it as an undergraduate, I'm not sure. I had no idea what this meant, but I copied it down faithfully in my notes. I have to tell you, I only figured this all out last week. I was very pleased. I just somehow was kind of vague, you know, sort of, you know how it is.
Can't you also, sorry, this would be a section of the line bundle where the transition functions are the absolute value of that?
Yes, I didn't actually write that down, but that's exactly correct. So there are two other definitions of what a twisted end form is. So the first is, which I'll state on the next slide, the twisted end forms are sections of a one-dimensional fiber bundle. And what's the fiber at any point? Well, the fiber at a point x is the space of all maps from the wedge product here. So they're in the dual of the tangent space, after all, the wedge product of the tangent space, the covectors to R. But now the forms, the end forms at x, are the linear dual, so everything works out well. But now the twisted end forms have this property. If I multiply a vector by a scalar, then I get the absolute value of the scalar out. So it seems a little odd. These are not linear functions. These are sort of, I don't know, half semi-linear or half linear functions or something. They only satisfy half the property. Nonetheless, this is a perfectly good one-dimensional vector space. If I have one of these things, I can multiply it by scalars. It's still such a thing. So that's what so there's a canonical definition of what the fiber at any point is. It's scalars which transform by the absolute value of the scalar. Yeah. So that's the canonical definition of what the fiber at point x is. And now, as he points out, what this means is, in practice, if you have a bunch of coordinate patches and you want to construct a twisted end form, what it means is you've got transition functions which are the absolute values of the Jacobian. So I didn't write that definition down. I thought about it, but I'm glad he brought it up.
Can you do this for lower degree forms, less than n?
I'm not going to say anything about that. There is such a notion of twisted forms also, but it doesn't play the same role, although it does. Yeah, I just don't want to say anything about it. Okay. And your homework exercise, not your quickie quiz question, but your homework exercise, is that on any manifold there always exists at least one twisted end form that never vanishes. So that's really the right thing to do. Okay, everybody, okay? There's nothing to do offhand with SL2. Okay, no questions at all. It's pretty nice, actually. I was very pleased with this. I have to say, I straightened. You know, at my age, you feel it's time to straighten everything out before you go to heaven. So when they ask you, what's the twisted end form? There I am, I'm all set. I can just point to the internet. Now, let's look at some examples. So the way to get examples, I want to look at homogeneous spaces. Now, homogeneous space is one which a group acts and it acts transitively. So the place where this is, in fact, it actually occurs throughout this whole course. I'm going to write my action on this side. So G is a Lie group, and H is a nice subgroup closed, which is also then a Lie group. Okay. So I want to look at twisted end forms on such a thing. Now, I want to look at arbitrary fiber bundles first. And this, one of my co-authors got really excited and gave me a long lecture why I shouldn't do this. There's some spelling mistakes on this. There are lots of spelling mistakes. It's getting later. It's about 12:30 by now. There's one there and there's one there. Let's see. I'm glad there are not 3 S's in associated. That's pretty good. I don't know. If you see anything else, let me know. So if I want to construct fiber bundles, in general, if you have a homogeneous space, and this is going to come up later on anyway, so this is a valuable idea. If I have a homogeneous space, you want to construct fiber bundles with the G action. Now, I'm not going to explain the details of this. But basically, the point is that, as you can see from a lot of examples we've seen so far, you're going to construct representations of SL2 by letting them act on sections of a bundle of some kind. That's the thing. In order to do that, you have to construct the bundle has to have some nice homogeneity property. And the way to construct such bundles is as follows. First of all, we take a representation of H. So we have G and we have H. We're looking at the quotient, G quotient H with H on the, there's some technical reason why we put it on the left rather than the right, which we've done so far. I take a finite dimensional representation of H, and I want to construct a bundle which is associated to that somehow. And what I do is Yeah, and the fiber is supposed to be at least non-canonically isomorphic to U. Now, of course, you know how to define fiber bundles probably by patches, but this is not the right way to do that in this case. In this case, it's a very nice sort of canonical construction. I take the quotient, I take the product of U and G, and I just let H act on the left on that. H takes, yeah, there's some missing things here. But anyway, H takes this to this, and that's a nice action on the space, and I just take the quotient. The quotient is perfectly well defined. It's a free action, and I just take the free action is made free by the fact that it acts freely on G, and so I just take that quotient, and that becomes a fiber bundle. And I'm not going to give all the details. This is what my colleague got really excited about. The sections of this turn out to be something like an induced representation. So the sections are the functions from G to U, such that f of hg is sigma h fg. So that's exactly how the induced representation was defined in case G and H were finite. I can't remember if Dragan has defined induced representations. I don't think so. But Peter defined these for the finite groups. Okay. And what I didn't write down, it's 12:45 at this point, and G acts on this. So if we have, so G acts on sections. So if I have hg, f of hg equals sigma of h, f of g, then, and if I have x a member of G, then R x of f is in the same space. And Rx of f of G is equal to f of gx. And this is the x-axis on the right here, but there's some covariant. This is a left action. R stands for right. See, remember, there's the right and left regular representations. Oh, no, that's perfect. Second line. Oh. No? There we go. Okay, sorry, yeah, okay. Right, what's R? Good question, what is R? R is a figment of my imagination. Okay. Right. So I'm not proving this. So there's something to be proven. It's kind of a nasty calculation, actually. But anyway, so the basic fact is I construct my quotient space, that's easy, to identify the sections of that bundle with such functions is sort of a slightly nasty calculation, in which I wasn't ready to do at 12:50 in the morning, so I just let it go, and that you can think about it. Now, the most interesting representation in a sense of H is that on the tangent space of, I say one, but I just mean the coset. So the G quotient H is not quite, well, it has a given identity element, so to speak, and that's the group H itself. That's a coset of H, and that's H itself. So there's sort of a best choice for base point on that quotient. And I have the tangent space of that. And of course, the tangent space is just the quotient of the Lie algebras, G quotient H. And H acts on each one of these spaces by conjugation. I don't know what we said about Lie algebras. We're sort of sweeping these things under the rug. But in SL2, a matrix goes to this. And this is the adjoint action. Okay. So that conjugation is the adjoint action. And H takes H into itself, so H also acts on the quotient. And the bundle associated to that action is just the tangent bundle. Now, there's another representation, which of course is the one I want, and that's the one that corresponds to measures on the quotient. And that's H goes to the absolute value of determinant of the adjoint action. And -1 because it acts by the determinant on the wedge product and the covectors, and it acts by -1 on the dual space. And so the associated bundle there is twisted N forms. If I wanted N forms, then I would just remove the absolute value. So the whole lecture so far is just designed to get you to understand that if I want to talk about measures in an invariant sense on this quotient, G quotient H, then there's sections of an associated bundle which can be identified with certain functions that satisfy some covariance property with respect to the left action of H. Okay? That's all. You can summarize. You can forget everything else if you're willing to believe that. So the whole point of the lecture so far is just to get you to realize how that works out. Okay. So if I want to integrate, so what I integrate on the things that I'm allowed to integrate on this space are the sections of this bundle. There's a canonical, not quite canonical because I'm making a choice of base point here, but an almost canonical, up to some scalar in a sense. There's some modest choice of something. As I say, it's not quite canonical, but it's almost canonical. Way to integrate functions on this. And in particular, it's G covariant. So I have a G invariant integral, so to speak, on the set of densities of sections of this bundle over that space. Okay, let's look at the example. I think what's next is the example I have in mind. Yeah, the only example we really care about is SL2. I'll say something about other SLNs in just a minute because they're also interesting. So if I take G equals SL2R, I take H equals P, that's the upper triangular group. Then the quotient of the Lie algebra, G quotient P, this came up in Peter's lecture yesterday when he's talking about Verma modules. The quotient of G quotient P is isomorphic to n bar, the opposite. And so the adjoint action on the covectors, well, the covectors are just one dimension because it's just as a one-dimensional space. The action on n bar is a to the minus 2. And so the action on the dual of that is a squared. And so the bundle of measures on G quotient P is the sections of a line bundle associated to this character of P. Now, in this case, a squared is greater than 0. So it's the same, this G quotient P. Well, G quotient P is just a circle. It does have an orientation. So there's no question about the orientation question, but still the point is that this is not 1. There's no invariant measure there's no G invariant measure on the projective line. You have to look at these densities or measures instead. Okay. Now, what happens for other n's, it's sort of interesting to know. This is not a totally vacuous theory. If I look at other dimensions of n, then for n odd, the projective space is oriented, but if I look at n even, like P2 of R is not oriented. I won't go into that. That's not too hard to explain, but it was an easy way to see that. But you're familiar with the fact the projective plane is not oriented. It's like the Möbius strip. It doesn't have a canonical orientation. And that continues on for parity n. Okay, so in that case, it's a quite non-vacuous theory. Okay, at any rate, we have a smooth, real twisted n form on this. It's something we can integrate, and it may be identified with a smooth function. Width is another thing missing here, from G to R, such that f of pg is delta p of p of f of g. So those are we can identify the things we can integrate on that. So there exists a G invariant measure, so to speak, on this, not measure, but a G invariant integral of such densities. Okay. Is everybody still with me? So the things I can integrate are functions which satisfy this equation on G.
Obviously, this delta P corresponds to that.
Delta P is a character of P. That's the adjoint action on the dual of the covectors on G quotient P. I can identify the sections of the fiber bundle of that, that's a fiber bundle. I can identify sections of that fiber bundle with functions on G itself which satisfy this equation. Right? That's the way associated bundles work. I take a representation of H. This H is P in this case. In order to get associated bundles, I take a representation of H. In this case, it's a character. And the fiber bundle associated to this representation of H is the twisted n forms. And the sections of this bundle can be identified with functions that satisfy that equation.
Yes, but why does this character give twisted n function, not some other character? Why is this the character which gives twisted n function, not
I'm sorry, I just can't, there's a noise.
why is this the character that gives me a twisted n function, not some other character?
Oh, because it's the thing, it's a, so let's look. So here we have P quotient G. This is isomorphic to n bar, right? The opposite n. And H is P. Now, what does P do on, well, P doesn't act on this piece. P acts on here. And n acts trivial in this. So A takes 1x1, goes to 1a minus 2x1. So wedge 1 of add action, the action on wedge 1 of Tx is isomorphic to n bar, and the action of P on this space, Px, by taking x goes to a squared x, if P is equal to ax 1 over a. Right, do you agree? You agree so far? So this is the tangent space action. Now, for twisted end forms, I want the absolute value of the dual action. There's no problem with the absolute value because it's a squared, and so the dual action is, sorry, this should be a 2. It's a minus 2 because it's a minus 2 here. So the dual action is a squared. And that's what I define to be my delta character, delta P. Now, it happens that this is also the adjoint action on this thing, but in some sense that's an accident. What you're really interested in is the inverse of the adjoint action on this thing. Okay, so that's another slight confusion. Is sort of canonically speaking, it's the adjoint action on this thing, but it just happens to be because of the way the group is structured. This is the same here. So it looks like this is this. It happens that it is this, but really what you're looking at is the inverse of the action on the opposite thing. And those are the end forms, twisted end forms. So as I say, for SL2, the positivity, the orientation is not a problem because this is positive, so everything works out fine. It doesn't make any difference whether I put absolute value around this or not. Okay. So these are the things I can integrate. So let me write down the theorem, which I didn't quite write down. So when I'm all through, I get the fact that there exists an integral. So there exists a G invariant integral, functional, linear function from the space of all f of C infinity functions f such that f of Pg equals delta P of P by f of G to C. And what G invariant means is that if I take the integral of this, this is homogeneous after all. I've constructed it so it's a homogeneous thing. And this is equal to, I have a homogeneous action that works like this. So if I take one of my twisted end forms, it's a homogeneous bundle, I can transform it by something in G, and the integral is the same. Yeah?
So is this delta the same as the modular?
Yeah, again, it's the modulus. It is the modulus character, but as I say, that's somewhat deceptive because it's really the inverse of the character on the dual space, on the opposite parabola. It happens to, but again, it is always for all semi-simple groups. It's always the modulus character of P on the thing. That's exactly right. Okay, so now we have this abstract integral, and the question is, what is it? How do we actually integrate something? And the answer is a very practical tool, namely, the quotient, G is equal to pk, so the quotient of G, quotient P, is also, separated my lines here, it's the same, k acts on this space, k is SO2, and it acts on this space with an isotropic over plus or minus 1. And so what happens is that if I assign k a total measure, and the integral is certainly k invariant because it's G invariant, and on k, on the other hand, we have a Haar measure. So my integral, if I take my form, if I take my function, I restrict it to k, and I want to actually integrate it, then I just integrate over k. See, everything's got a little bit of this. There's no canonical choice of the. Once I've identified the functions, there's no canonical choice of these things because there's some up to scalars. But I can. This will work. So I know that there is a G invariant one. The G invariant one has to agree with the K invariant one, and that we can construct easily a K invariant one, namely just integrate over K. Right. And so when I'm all through, no, not quite. I'm not quite through. There's another way to put this. So if I take a smooth function with compact support on G, then I can integrate it over P with respect to a left measure. And integrating with P with respect to a left measure is easy. I'll say something about that in just a moment. Again, you can write down explicit formula that's written down here. Anyway, this gives me, if I do this, it turns out, you can verify it yourself, that this is a density. This new function g, so I start off with a function of compact support on g, I integrate it over p with respect to a left measure, not a right measure, but a left measure, and it turns out that that satisfies the right functional equation, and this is a density, or a measure on g quotient p. So I can integrate that, and if I say there's some choice of normalizations, but if I choose constants right, then the integral of f over g is also equal to the integral of f bar over g quotient p. And the reason that works out is because I know that the left invariant integral works out all right, so if I go through this process, so it has to agree up to scalar, and so I just have to choose the measures right, so that I have to choose normalization, I have to choose the measure on g correctly so that this works out. And I can write this like this. This is again with left invariant, there's a measure, you can check that this is the way to integrate with respect to the left measure on p, and so my final formula becomes integral of f of g over g is this integral over the triple product k-a-m. Okay. I have a feeling I've lost a few in that process. That's actually the only elementary part of the talk, but I have a feeling somehow I lost a few people. Are there any questions? So this explains this integral formula in some sense. I mean, it doesn't, but this is another more important thing in both. Okay? Now, it's not going to play a role here in today's lecture. Not much is going to play a role in today's lecture. There's another way to integrate. So one of the whole points of this is the following. We have this g invariant integral over the measures on the projective line. And now we have one formula for it in terms of integrating over k. But it turns out that that's convenient sometimes. There are some situations when that's when you, and we're going to see a lot of explicit integrals pretty soon. And so that's one way to do the integration. You just integrate from 0 to 2 pi, because that's what integrating over k involves. We're going to see a lot of really explicit integrals. But that's not the only way to integrate. The other way to integrate is the following. We know we have this Bruchau decomposition, and a slight variation of it, which I mentioned in my first lecture, is we have p times n bar. That's a huge open set in G. And if I quotient out by p, then I get a copy of n bar. So we have a copy of n bar sitting in p quotient G. And of course, we get that by stereographic projection. We've seen that already. So here's G quotient P, here's infinity, and here's my copy of n bar sitting in there like that. Now, my G invariant integral is also n bar invariant. So my G invariant integral on my densities has to be the same as just integration of the function over n bar, up to some scalar again. And so there's some scalar such that this is also the way to integrate. And so now we have two different ways to integrate a given function in my densities. I can integrate it over k, or I can integrate it over n bar. Now, one problem which arises is it's not quite obvious that this integral even converges, but we'll see that it does. And so this is a second way to integrate. One question, which is really a beautiful question in a way, is what's the relationship between the two integrals? So we have, let's see, we have an integral over the circle, or actually half a circle, because k is only half of k appears here. We also have an integral over this, and it turns out the relation between the two integrals, one's pi times the other, namely half the circumference of the circle. We'll see that later on. Yeah, I always choose normalization. So on R, I certainly choose just the usual hard measure, usual Lebesgue measure. And on K, I choose a measure such that the total measure of K is 1. And I identify n bar with x just by putting an x down there in the lower left. You're right, it's true, but there's sort of an obvious choice in a sense. Okay. Now, there are several reasons why this is important, but the main reason why this is important is because if you're interested in doing automorphic forms, then K isn't so well defined. If I'm doing automorphic forms and I'm working with a group over Q, and I want somehow a differential form on the whole group, which works for every one of the p-adic fields, the real fields, and so on. And so the way to do that is to define, on the other hand, the factorization, the Bruchau factorization still works. So it's still true, even over Q, that G is equal to this. So you choose, if you want to integrate automorphically, so to speak, then you choose an n form that's compatible with this factorization. So this is, in a sense, the best way of integrating, because it's defined globally. It's not just something specific. If I choose a maximal compact, that means I'm really working with R. I can't work with the other p-adic fields at the same time. Okay, so we'll see later what the constant is. And now my talk is just beginning. I guess I'm going to stop. Let me say just a little bit word about it, because I have just a few minutes, so give me about 3 minutes. So I'm going to introduce principal series. And principal series are sections of bundles on this which are homogeneous. So again, principal series are going to be, they're going to be functions on G which satisfy some transformation property by P on the left. But they fit into this lecture because they're just sections of some bundle, homogeneous bundle over the projective line. So that's again the other tie-in, and that's why I made this slight digression on homogeneous bundles. Okay, that's it. And I've gotten to page 18 out of 30, oh, it's 48 pages here, so okay. I'm not going to get through even the second part of the lecture today. My second lecture will go through, start and define the principal series. Okay, I'm all through for today.